Hello everyone. Today we are going to be talking about complex numbers and how you can get used to complex numbers, as well as we are going to be dealing with some of the basics of complex numbers. So this is going to be an introduction to complex numbers. Now, I pose to you a question. Find x such that the square of x plus 1 is equal to 0. If you try to solve this for x, you will get x is equal to the square root of minus 1. Now I have a different problem for you now. If this is the real line, so it goes from minus infinity to infinity, and in the middle there's 0. There are numbers, of course, 1, 2, so on and so forth, minus 1, minus 2, and so on and so forth. Of course, this also includes numbers such as, 1.5 or 1.45, and, basically every single number that you've ever known. Now, I want you to plot this in this line. So I want you to find square root of minus 1 on this line and plot it, which you will not be able to do because this number does not exist on this line. So the square root of minus 1 does not exist on the real line. Now, because this number does not exist in all the numbers that we know, new numbers were invented in order to provide a solution for equations such as this. So mathematicians invented something called imaginary numbers. Now, what imaginary numbers are is they're essentially a completely different branch numbers. So they're a different branch of numbers from real numbers, and are made up the imaginary unit iota. So, this is equal to the square root of minus 1. And you could say that this imaginary unit is the 1. So this is equivalent to 1 in the imaginary world. So you could picture the set of real numbers and the set of imaginary numbers as two different worlds. And these two belong to something that is bigger, which is complex numbers. So all real numbers and all imaginary numbers are complex numbers, and including everything in between, which is a combination of both real and imaginary numbers. So all of these numbers are complex numbers. So I should now introduce to you about a few more features of the imaginary unit iota. So since we have that I is equal to the square root of minus 1, we have that I squared is equal to minus 1, and I cubed is equal to minus I, because this is equal to I squared. This over here is equal to I squared times I, and I squared is just minus 1, so minus 1 times I is, minus I. And following the same logic, which is I squared squared, we have this is minus 1, so this is actually equal to 1. Now, the interesting thing about these powers of I is that these cycle, right? That's a very interesting thing about the powers of I, and it's that the powers of I cycle. So we have I, we have minus 1, minus I, 1, and then I. So if we multiply by I, this keeps cycling and cycling around. And for example, if I told you to find I power 37, how would you do it? Now, you could essentially multiply by I, up to, 37 times. However, there is a much neater way to do this. And how to do this, you ask? We can write this as I power 36 times I, which is I power 4 power 9 times I. Now, by this, we have that the fourth power of I is just 1. And, well, since this is 1 to the power of 9 into I, which is, 1, so 1 into I is just I. So it was easy as that. And if you notice something here, we are using the fourth power of I to decompose a greater power of I. So what you could do essentially is, if you are told to find the value of I power n, you could calculate n mod 4. And if n mod 4 is equal to 0, this implies that I power n is equal to, well, you guessed it, 1. If n mod 4 is equal to 1, this implies that I power n is equal to I. If it's 2, this means that I power n is equal to minus 1. If it's 3, this means that I power n is equal to minus I. So this is a neat way of finding the powers of I. Now, this was all we need to know about the imaginary unit in order to understand some of the fundamental things in complex numbers. Now we move on to complex numbers themselves. So complex numbers, essentially, purely complex numbers are a combination of both real and imaginary numbers. So complex numbers are a combination of both real and imaginary numbers. And for example, if we have a number, let's say we have a complex number z, we can essentially write this as a plus I b. This is the real part, and this is the imaginary part. Now, to denote the real and the imaginary part, we use the notation Re of z for the real part of z. And this is, 1, a, and we use Im of z for the imaginary part, which is b. So this is one of the main ways that we denote complex numbers. We also use ordered pairs. So if we have a complex number, let's say w is equal to c plus id, we can write this w also as an ordered pair, such as c, d. This, of course, being the real part, and this being the imaginary part. Now, because we can write this as an ordered pair, we can also visualize this on a graph. And this line over here is called the real axis. And this line over here is called the imaginary axis. And altogether, this entire plane is called the complex plane. Now, remember that I taught you I is the equivalent of 1 in the imaginary world. So, the thing with numbers is, for example, if we have a real number, such as, let's say, 2, we can write this as 2 times 1. If we have an imaginary number, 2i, this is 2 times I. So 2 is the real counterpart of 2i, and 2i is the imaginary counterpart of 2. So this one and this I are just, well, they're the same thing, right? They're the same thing, except they're in two different worlds. One is in the real world and one is in the imaginary world. Now, moving forward, I'd like to introduce some properties of complex numbers. So let's say that Z1, Z2, Z3, and W are four complex numbers. We have the properties, for example, that Z1 plus Z2 is the same as Z2 plus Z1. This is the first property, and it's known as the commutative property of the addition of complex numbers. Now, after that, we have something called the associative property, which is which is Z1 plus Z2 plus Z3 is the same as Z1 plus Z2 plus Z3. This is the associative property of addition. After that, we have the commutative property of multiplication. If we have Z1 times Z2, this is the same as Z2 times Z1. After that, we have the associative property of multiplication. So if we have Z1 into Z2 into Z3, this is the same as Z1 into Z2 into Z3. So these are all basic properties that are also true for real numbers only. And in fifth number, we have the distributive property of multiplication. So if we have, let's say, Z1 times Z2 plus Z3, for instance, this is the same as Z1, Z2 plus Z1, Z3. Now, this is, well, I guess this covers most of the basics regarding the algebraic properties of complex numbers. Now we go to some algebra. Now, adding, let's say, addition of complex numbers is pretty straightforward. So we've already learned that we can use A plus IB or C plus ID to denote the real numbers, or rather the complex numbers. So we can use these to denote the complex numbers. So if we were to add A plus IB and C plus ID, we would have A plus C plus IB plus ID. And this is, well, just regular addition. And A plus C plus I times B plus D. Now, if these were expressed in terms of ordered pairs, we would have A, B, and C, D. Now, if we add these two ordered pairs, we have A plus C and B plus D, which is the same thing that we obtain via this way. So if we express this as an ordered pair, we get the same thing. So A plus C and B plus D. So yeah, this is how you add complex numbers. So moving on to, I guess, would be multiplication. Now, the same thing is true for addition and subtraction. So yeah, but for multiplication, let's say we have two numbers, A plus IB and C plus ID. We just multiply these algebraically. So we multiply these two, so AC plus, I guess, IAD plus then these two. So IBC plus I squared BD, which is then equal to AC minus BD, because notice that this is the square root of I, which is -1. So AC minus BD plus I times AD plus BC. Now this simplifies to AC minus B, or I guess we could write it as AC minus BD and AD plus BC as an ordered pair. Now this is also, I guess you could call this a formula. So AB times CD is equal to AC minus BD and AD plus BC. Now, moving forward, I'd like to introduce division. So if we have, let's say, two complex numbers, z1, or rather z, let's say a plus ib, and w equals b, or rather c plus id, and we want to find, let's say, z over w, well, provided that this is not equal to 0. Now, to find this, we can write this essentially as z times w inverse. Now, in order to understand the further steps in this, we will need to find the inverse of w. To do so, we will take, so w is equal to c plus id, and which implies that 1 over w is essentially 1 over c plus id. Now, what we do now is we multiply by the conjugate of this. So c minus id over c minus id. So by which we get c minus id over c squared minus I squared d squared. Notice that this is just the formula of the difference of two squares. Now, this then simplifies to c minus id over, notice that this is -1, so this simplifies to c squared plus d squared, from which we get c, rather, maybe not right over here, so over here, which simplifies to c over c squared plus d squared minus id over c squared plus d squared. So from this we have found that the multiplicative inverse of w is c by c squared plus d squared and minus d by c squared plus d squared. This is the multiplicative inverse. And in order to find the division, which we were finding over here, we need to multiply z with w inverse. Now, this I'll leave as an exercise because it's relatively simple. We just need to use the same rules that we did in, finding out the multiplication of two complex numbers over here. So I'll leave this as an exercise. It should be relatively simple. And I guess I should give you some problems to try. So, I want you to find the value of, let's say, I power 37 plus I power 21 plus I. So what's the value of this? The second problem will be multiplying, let's say, 3 plus 7i into 2 plus, or rather, I should give this as ordered pairs. So 3, 7 multiplied by, let's say, 7, 20, or rather, let's just use 7, 2. So how much is this? And I also want you to find, let's say, 2, 1 divided by 1, 2. And I think this should be this should cover everything that we've learned right now. So this was a very elementary introduction to complex numbers. We haven't really dived into anything fairly complex right now. So I do hope that you have enjoyed this video. I have tried to make it as simple as possible, and I hope you enjoyed. Yeah, thanks for watching.